just attended our basic course on Jamovi, it will be a repetition for you people. But still, just to start with, we will start this session with the correlation. So generally, what is a correlation? Basically, whenever you want to see the association between the two continuous variable, that we mean by the correlation. So this learning objective, I have already told you, but still just as a part of this slide, we will learn the concept of correlation and simple linear regression. Then we'll perform the correlation and regression analysis in Jamovi. Then we'll see how to interpret, because interpretation is very important. Then only you will be able to write your result and to understand what are the how do you control for variables, how do you treat a variable as a confounder or not as a confounder, and then how do you interpret the beta coefficient of a regression, what is the meaning of intercept. So all these understanding of the equation and the concepts, we'll see how to interpret that. And then we'll again see what is a residual, how to do the plotting of various residual, and how to check for the assumptions. Because in regression, in all these, like today and tomorrow, regression is basically it's like a prediction. You want, based on some equation and data, you want to predict something. So unless and until you check for the assumptions, your model will not be accurate and there will be a lot of errors. So that's why we want our all assumptions to be checked and it should satisfy. Then only you can perform a linear regression. I'm talking of linear regression today and tomorrow. So in this correlation, we'll see what is the basic of this correlation, what are the various research questions for which we need correlation. We'll also see what is a covariance and what is the difference between the covariance and correlation. Because from covariance only we derive this Pearson's product moment correlation, which is R. And then what are the assumptions and hypotheses? Because we know from our descriptive background in the basics of Jamovi, you know that basically we perform two types of analysis. We perform a descriptive analysis and we perform a inferential statistics. In descriptive, what we do, we generally describe the data in terms of like what is the range of the data, what is the central tendency of the data. And central tendency, we talk in terms of like mean, median, and mode. Then we see the dispersion of the data. I'm just revising because again, we will be doing the descriptive here, because descriptive is a must do for any type of analysis where you check for the variables, the type of variables, the missing data, any outlier, all those things you check in the descriptive. So in descriptive, you see the generally 4 types of descriptive we do. We do a frequency table where the data is categorical, and if the data is continuous, then we basically see the central tendency, we see the dispersion, where we see the standard deviation, variance, we see the exact position of the data, which is like the centile, which can be, depending on your need, it may be a 5th, 95th, or 25th, 50th, and 75th percentile. So, and you also check for the normality of the data. Depending on the sample size, you may perform a Shapiro-Wilk if the sample size is up to 50, or you may perform the QQ plot if it is more than 50. You can also use the histogram and density plot. So maybe for those of you who are joining this session for the first time, I'm just revising the previous basic Jamovi. So you can again go back and see those sessions of descriptive statistics where we check for all those variables. So those are important part of this linear regression also. And then we'll see how do we interpret the commands which we have performed, and then I'll be summarizing it. So starting with the research questions. So, and again, you please go back and revise your concepts of variables also, because here also we will be talking about that categorical variable, the continuous variable, what is a scale variable, what is a discrete variable, because again, the same functions you need to do here also. So again, please, like today we'll be posting this recording also, but revise your concept or refresh your concepts. I'll be telling you in between also. No, if you don't get time, that's okay. But still, if you revise, everything will be fresh in your mind and you will be able to understand more. This because this is a little one step ahead of that basic analysis, where here you are performing the modeling, you are performing the predictions, you are doing the predictions. So for that, basic should be in place. So the research question is like, if you want to know the relationship between the two variable, and here you can see that serum vitamin D and the serum calcium level, both of these are a continuous variable, and you want to see the relationship between these two variable. So for that, you may perform correlation. If the two variables here, if you want to know between the relationship of sleep duration and the percentage of marks obtained in the final examination of MBBS students, still you can perform this correlation. Or if you want to see the relationship between the female literacy rate and the infant mortality rate, then you can perform this correlation. So in all these research questions, what we have observed, that there are two continuous variable. We call these variables as a scale variable also. All these like ordinal and the uh, continuous variable, we call it as a ratio. So there are two types, interval and ratio scale. These two variables clubbed together, we call it as a scale variable. So in all these, or a continuous variable, because so in this case, there are the two variables and they are related. How they are related to each other, this we appropriate statistics which we perform is the correlation. And since if it is a scale variable, we go for the Pearson's correlation. In case of an ordinal, instead of Pearson's, we go for a Spearman correlation. Or if the data is again not normally distributed, which we'll see in the assumptions section, then also we go for a Spearman. But again, if the data is normally distributed and if it is a scale variable or a continuous variable, then the appropriate choice of statistical test is the Pearson's correlation. Now, understanding that again, it is a repetition. What is a covariance and what is a correlation? So it is like this correlation concept is derived from the covariance. So what is a covariance? Basically, so here in covariance, if you see the term, there are two terms, co and vary. So there are two terms. There is a first term, which is the co, means together. And variance means like vary. Vary means how it is changing. If you change one variable, how the second variable is changing. So this is how you see the concept of covariance. So in this data set, if you see this data set, there are two, this is the data of 5 people, where you can see in the first column, it is the number of person. And in the second column, it is the exercise hour, which is measured in the hours. And then it is the resting heart rate. So if I have this data on the number of hours of exercise per week, and I have taken the heart rate of these people, and I want to calculate the covariance between the exercise hours and resting heart rate, which is like per 70 beat per minute. That's the unit. So how these variables are co-varying. So for that, what I'll do, so in this, just one thing you can see here, that as like I think you can see this data for a few minutes, then you can understand what I'm talking. You can see the exercise hours, like it is decreasing, 3 2, again increasing like 4 5 and 1. And if you see the resting heart rate, it is like 70 75, 68 65 and 80. So you can see, like, if the number of hours are more, the resting heart rate is less. Again, you can see if the number of hour is less. In case of here, the number of exercise hour is 1 and the resting heart rate is 80. So you can see, like, if the number of hours are decreasing, the resting heart rate is increasing. So you can see, like, there is a direction. Direction means it is, if one is increasing, or the other is decreasing. And that you can call it as inversely proportional, or you can call it as like a opposite direction. But if I want to know, like, how, by what amount they are like co-varying, then I need to perform a few calculations to understand that. So how will I do that? So for this calculation of covariance, I need to calculate the total, we need to calculate the mean of this value, and then we deduct it from the individual value. So if I see I will calculate the x, which this variable is the exercise hour, and this y is the resting heart rate, which is my dependent variable. So we will, in this regression, we always put x as a predictor variable. Predictor means this is my independent variable. And in the section of basic GEMOB, I think we have covered this, like what is a dependent variable and what is an independent variable. So dependent variable is something which you want to predict, and independent variable is something which is also, we call it as a predictor variable, with which you are predicting the dependent variable. Since you are predicting the resting heart rate based on exercise hours, so in this case, the resting heart rate will be your predictor variable. The resting heart rate will be your dependent variable, and this exercise hours will be your predictor variable. So if I have to calculate the covariance, how will I do that? I will calculate the mean of this x and mean of this y. So mean of x is 3, you can see here, and mean of y is like 71.6. Then I will calculate the distance from the mean, the individual value. So I will just reduce this, like deduct this 3 from each of this individual values. So here the direction, the sign will be there. Like here you can see this minus 3, and here it is plus. So in this case, if you can recall the variance, there also what we do, we calculate the distance from mean, but we square it. But here you don't have to square it. You just calculate the distance from the mean, and then you sum it up, and then you divide, and those summing up is like the covariance. So again, in if you just see the deviation from the resting heart rate, this variable, this mean, what I did here, I have deducted the individual, this mean from the individual data set. And so that's why here also you will see that minus sign is here, and here also it is a minus sign. And then what I did, I have taken I have multiplied these two values, like this 0 and this 1.6. So this this is the delta x and this is the delta y. And if you multiply these two and then sum it up, so this 37 is what? This 37 is the summing of these all values, and here it is a minus sign. Because if you see, this is minus, this is minus, this is minus, and this is minus. So everything is minus. So this is minus 37. So if I have to conclude that what is the covariance, then the covariance is minus 37, which is like why minus? Because you see that when I'm increasing the exercise hour, the resting heart rate is decreasing. So this is showing the direction also. Negative means like if you increase one variable, the other variable is decreasing. So this is the covariance. Okay, and this we use in case of scale development. This thing also, those of you who have attended it, you know that we measure the covariance between the two items. And there also we use the product moment correlation. But again, this will have a unit. Why? Because you see that this is measured in as a heart rate beats per minute, and this is as hours. So it will have a unit, and we get the total covariance by adding these multiplied like product values. So what is the property of covariance? So basically, we say that if the two variables x and y, and what is x here and what is y here? So x is your independent variable and y is your dependent variable. So if x and y are entirely unrelated, then the amount of this covariance will be 0. If the x and y are positively related, then the covariance value will be positive. And if x and y are negatively related, then the covariance value will be negative. But again, this is a raw value. Why? Because here there is a unit attached to it, and we cannot interpret it easily, as it is dependent on the units in which x and y are expressed. So that's why when you divide this, again, this question is, can you tell the unit of this covariance here? I've already told this probably that it will be hours into beats per minute. But again, how to get this meaning of covariance? Because if I say minus 37, it does not tell me the intuitive meaning. So what I did generally, you standardize this covariance value. And when you standardize it by dividing it by the product of the standard deviation of these two variables, then it is known as the Pearson's correlation. So total covariance, which I calculated, that was minus 37. And when in the denominator you take the standard deviation of x multiplied by standard deviation of y, then it is known as the Pearson's correlation. And since it is a product means multiplication, because you have multiplied and you have taken a sum of it, it is also known as the Pearson's product moment correlation. And so that's how this we have this told you this. Why? Because you should understand, in all this regression we will be using this concept of R and R square, which tells you about the, the predictor, how much the predictor is telling you the variation in the dependent variable, R square. So that's why you should be able to understand what is this R. So this is R. This R is basically the, when you square this R, or the product moment correlation, which we also call it as the coefficient of determination. This is the R square. So how we calculate it? Again, to summarize, you have got this X and Y variable. Y, in all the regression, Y sign is used for the dependent variable. And X is used, X, if there are many, then we use X1, X2, and X3. So X is the terminology which we use for the predictor variable or the independent variable. So if you just calculate the distance from the mean, multiply these two and take a sum of it, that is the covariance. If in the covariance you divide it by the standard deviation, product of the standard deviation of X and Y, then this whole value is known as the correlation. And correlation, it tells you, it is now standardized. So again, you can compare. That's why you will see that correlation doesn't have a unit. You only say that value of R, it is like 0.5, 0.6, or 0.3. It doesn't have a unit. Why? Because then you can compare. Because in covariance, it has got a unit, so you cannot compare it with any other. But here you can compare. So this is used to determine the strength and direction of linear relationship between the two continuous variable. But again, if you make categorical variable out of continuous variable, like if you make this vitamin D take a cutoff and make a two categorical variable like less than 10 and more than 10, like in this case, or if you like take a cutoff of 5 serum calcium level and make a continuous variable into categorical variable, or even the sleep duration and the percentage of marks, if you like categorize it, taking the cutoff of 6 for sleep duration and 50% for marks. And similarly, like female literacy categorical as low and high and infant mortality rate as low and high, then again, you cannot calculate correlation, because here you have made a categorical variable. So for this correlation, the nature of the variable should be a scale variable. Now, what are the underlying assumptions? So the underlying assumptions are like there should be two different continuous variable which should be measured on like continuous nature, that is like ratio or interval, and it should be a paired value. Paired means it should be of the same person. And if you can recall your sessions on the basics of Jamovi, where we have calculated, we have learned the paired sample t-test, and we have also learned the McNemar test. McNemar we use for the categorical variable pre and post, but it should be from the same person. So that's how you should understand what is a paired value or a paired variable. Paired means it should be either from a same person or those two people. I mean, like if I calculate paired means like heart rate, in this case, heart rate and exercise. These two values I am taking from the same person. So that's why it is known as the paired value. Paired values or the paired variable. And the second assumption is like there should be a linear relationship between the two variable, and which we test here. Instead, in case of correlation, it is okay, but in case of a regression, you will see that generally we do all these analysis on residual, and we'll understand what is this residual is. If you can recall on sessions on basic GEMOV, the residuals are like the difference between the predicted and the actual. In case of a chi-square, if you can recall, we have learned that residual concept, and there that post hoc where you were like seeing in which cell that's there was a difference in observed and expected. So that observed and expected is again like a residual, because in chi-square also, when in that cell, when there is a frequency, you predict, like based on the null hypothesis, it will be like a predicted or the expected. There, instead of predicted, we use the term expected, and then there is a something observed. So difference between observed and expected. In case of a chi-square, the same concept is here also, like difference between the predicted and actual. So that's the residual. So in case of regression, or mostly all the normality or the assumptions we test on residual, because residual tells you regarding the variance, how much the data is varying, your predicted versus the actual one. And then the next assumption is like there should not be significant outlier, because regression or correlation, it is very sensitive to outlier. And in descriptive, we'll tell you here how to check for the outlier. Yes. In case of a descriptive statistics, all of you, I mean, those of you who have attended our previous workshop, you can just type in the chat box, how do we check for that? Or you can unmute and answer.
Madam, box and whisker plot.
Range will show you the dispersion of the data. Like lower.
Box and whisker plots.
Which plot, Dr. Geeta?
Box and whisker plots, madam. I mean, the quartile range.
Yeah, right. So this outlier in the histogram, Priyanka, generally you see the normal. For outlier, you have to plot the box and whisker. Yeah, true. Dr. Ajay and Dr. Sunil, you have correctly written. And then you need to satisfy the assumption of normality, because this Pearson's correlation coefficient, this is for the normal distribution. And if data is not normal, then we go for a Spearman. So what are the properties? You know that it tells you the, like we have seen in the covariance, this correlation coefficient also tells you the direction and the strength of relationship. So it measures the strength of linear relationship, and the sign tells you the direction, whether it is in the positive direction or it is in the negative direction. And the magnitude tells you the strength. So how to tell you the strength? So if it is, we'll see that values, but it ranges from -1 to +1. And the correlation, we know that it doesn't imply causation. For causation, there are other criteria, you know, that the Hill's criteria is there for say that, yes, is it this, is a causal or not? But again, yes, strength of association is one of the factor to say that it is causal or not, but it doesn't imply that automatically it is causal in nature. So causality is again another criteria based on which you say that something is causal or not causal. Coming to the interpretation of this R, if the value of this correlation coefficient is less than 0.3 but more than 0.1, then we call it as a small correlation. If the range is between 0.3 to 0.5, we call it as a moderate correlation. If it is more than 0.5, then we call it as a strong correlation. Now coming to the linear relationship. The linear relationship, we'll see, we check in the residual plot. But again, if you plot a scatter plot, and if like directions of these lines, you see here, this is a scatter plot and this is a line. So this line is basically the fitted line. And this fitted line is known as like the predicted values. So in all this linear regression, we'll come to that particular equation also. But if the it is like increasing, if it is like this, and it is increasing, if one variable is increasing, the other is again increasing. If one variable is increasing, the second variable is decreasing. So this is a linear, but in the other direction. But if it is something like this, like a parabola, or if the direction is something like this, or if it is like this, or if it is like S in the form of a S, then these are not the linear relationship. So in that case, you cannot go for a linear regression, because linear regression is only if there is a linear relationship between the two variables. Otherwise, you cannot, then you have to go for some other type of regression. And this is the coefficient of determination, which is known as the R square. So if you like square the this R, which is the correlation coefficient. So like, let's say if the correlation between the serum vitamin D and calcium is 0.55, 0.552, or the correlation between the sleep duration and percentage of marks is 0.702, or the correlation between the state literacy and infant mortality rate is minus 0.801. So these values tells us the direction and linear relationship. But if I want to know the variance in one variable, which can be explained by another variable, like the variation in serum vitamin D level from one person to another person can be explained by serum calcium level by what percentage, or the variation in the percentage of marks obtained from one student to the another student can be explained by sleep duration by what percentage, or the variation in the infant mortality rate in one state as compared to the other state can be explained by the literacy rate by what percent. So then there's something known as the coefficient of determination, which I was talking in the beginning also, like which is known as the R square. So you just square it. So like if you square 0.552, this will be like 0.30, and this will be 0.492, and this will be 0.641. So you can say like 30.4% of the variation in serum vitamin D can be explained by serum calcium, or the 49% means 49% variation in the marks percentage of a student can be explained by sleep duration, or the 64% of the infant mortality rate in one state as compared to the other state can be explained by the state literacy. So this is the variation or the coefficient of determination which you interpret as a R square. So null and alternate hypothesis is like the population correlation coefficient is equal to 0, and the alternate hypothesis like the population correlation coefficient is not equal to 0. So we'll see this once I'll show the demo of this. So I'll just explain, I have just explained this correlation. Once we start the demo of regression, I'll again once again perform these basics of correlations and few basic descriptive statistics also. So up till this point, everyone is clear on the concept of like what is R, what is direction, what is covariance, what is your assumption, and how do you interpret it? What is your coefficient of determination? Yes? Or anything do you want me to repeat up till this point? Can I see the chat? Otherwise, I'll go. Okay. So if it is okay up till this point, I'll go to the now sessions on the linear regression. So this, we were talking about the, is it necessary? No, the Bhavna, if you remember, it's not needed. If you know already the basics of statistics or basics of GEMOV, then it is not needed. If you have forgotten or if you want to refresh, then you may. It is up to you. So this, because GEMOV, I said that interface is very easy, user-friendly. So even if you have not done it, you will do it now and you will learn it. You don't, in GEMOV, I don't think you will forget because everything is written in front of you. You just have to perform. It is so easy and user-friendly that there are very less chances. You might, if you forget, then you may refer to those videos. But otherwise, it's not needed. I mean, not necessary. That's what you have asked. So coming to this linear regression, this thing in basic statistics, we have learned about the how to measure the association between two categorical variable, and we have seen the chi-square. And the chi-square we have learned like chi-square test of independent, chi-square test of homogeneity, and chi-square test of like good fit. So this those chi-square tests we have seen, but in all those chi-square tests, it was a categorical variable. In case of a continuous variable, we have just seen the correlation between how do we measure the correlation. So if any such correlation or association exists, then there you see only with one variable. But if there you want to exactly predict how the one variable or the dependent variable is moving or behaving, in context of an independent variable, then you perform the modeling or the advanced statistics. So in advanced statistics, we basically see like how to see these associations, how to predict the value of one variable based on the value of another variable, which is also known as generally we call it as a model the equation or model the variable or modeling. So, or the predictions. So there are basically three statistical technique, most commonly these three. There are many more, but for majority of us, if you know these three, most of your work will be done. So the most common statistical tests in the field of medicine is the linear regression, the logistic regression. There are types of logistic regression also, like binary logistic. There is a proportional logistic, and there's a multinomial logistic. In linear also, you have got a simple linear, and then you have got a multiple linear. And then the third, if there is a time dependent data, then you model using the Cox proportional hazard model, or basically we call it as a survival analysis. So we'll see the linear regression in this week, and in the next week we'll see the logistic regression, and probably next month we have the workshop on the survival analysis. So these are the three important techniques of modeling. So we'll start this with a simple example. We have given this example in logistic and many of the other workshops also. So you may find it as a repetition, but again, since by this you can understand what is a linear equation. Because for those of you, it's a little mathematical concept. Why mathematical? Because it has got an equation and you need to understand it. So that's why I'll go very slow so that you will be able to understand the residual, the difference, and various other assumptions. So this is like 5 data set you can see here and here. The first column, it is showing you the distance traveled in the kilometer, and the second column is showing you the taxi fare. Like for 1 kilometer, the taxi fare is 100. For the second kilometer, it is 110. For third, it is 120. For fifth, it is 140. And for second, it is 100. Again, if it is 210. So if I have to make a formula from this data, formula means if I want to predict, like let's say I want to predict the what will be my taxi fare at 10 kilometer. Then can you make a formula from this data? Or can you predict based on these 5 data points, like what will be my taxi fare if the distance is 10 kilometer? All of you, please try.
It will be 100 rupees extra.
100 rupees extra. But how, like, are you like saying it on the basis of any assumption or any equation?
Based on just assumption, ma'am. Difference for 1 kilometer is 10 rupees. So for 10 kilometers, it will be 100 rupees.
Okay. That's good. That's good. But again, like if you have to make a equation, that is, you are okay. I got your point. But like if you have to make it in the form of a equation, there will be some basic, like for 1 kilometer. If you apply the same thing for 1 kilometer, how you can write it?
100 plus 2x, 100 plus 3x.
Can you repeat it or can you type it? So basically, like Dr. Subhapriya was telling you, or the other people has also written, like 10 rupees. So if I make an equation, then this will be like, again, you rightly said that 10 multiplied by distance traveled. 10 rupees for each kilometer. Rightly said. But this is one, if I have to write it as an equation, so I'll write like 90 plus 10 into distance traveled. Yes, Dr. Aromal has written 100 plus x and 100 plus 2x. Okay, and x is your distance traveled. But
Distance traveled. Like 100
okay.
plus x, 100 plus 2x, and x is a continuous text like that.
Okay, so intercept in this case, then it will be not, because in case of a linear equation, that 2 or 1 which you have written, that should be fixed. Then only you can predict. Like in this case, this 10 is a fixed number. And then this distance traveled is changing. In case of your equation, it will be like 100 plus x, then 100 plus 2x, 100 plus 3x. Then this coefficient, that will be changing. And then this will not be in a form of a linear equation. So in linear equation, your prediction should be in the form of a linear equation. And what is a linear equation? Linear equation is equal to y is equal to a plus bx, where this a and b are constant. This a and b are constant. And the only two changing one is your x, based on which your y is changing. And in the correlation, we have made it a point, like, remember the terminology. Y is always the dependent variable. So in this case, my taxi fare is my dependent variable. So y is my dependent variable. X is my predictor variable or the independent variable, which is the distance traveled. So this A and B are constant. So Arumal, like in your case, if I go by your equation, then that B is changing.
Yes, sir. Yeah, and right.
Okay, so that's why, yes, it is in the form of an equation, but it is not in the form of a linear equation. So
Yeah,
your
yeah.
linear equation should always be where this A and B, it should be constant. And the only changing will be your X, and based on which you are predicting the Y. So everybody understood this, Subha Priya, how, like, you have correctly said it or written it. Probably Dr. Ajay has also correctly said it. But in linear equation, you give your prediction in the form of an equation. And that is like y is equal to a plus bx. So in all these, like today's and tomorrow, we'll be using this y is equal to a plus bx. This mathematical linear equation is like fitting your data. So by your data, the equation which the software is giving, it gives the coefficient which we write in the form of an equation. That is the purpose of your linear regression. Okay. So all this, you will see this B. What is this B? So this B is known as the coefficient. If you see this B is the coefficient. This A is the intercept. And this Y is your dependent variable. And this X is your independent variable or the predictor variable. So remember, this A is intercept. What is this intercept? Intercept is a constant, which is 90 in this case, and this 10 is a coefficient. So remember this term coefficient. We'll be using this term coefficient quite often now. So with this taxi example, you remember that there is something known as the intercept, which is like this A, and there's something known as the coefficient, which is this B. And these two are constant for any equation for one variable. Again, in multiple linear regression, we will see that this keeps on expanding. Like here, there is only one variable, but if there are multiple variables, we'll write like x1, x2, and x3. So with the help of this equation, can you predict the taxi fare for 5-kilometer distance? Yes. What will be the value of 5 kilometer? Can you predict it? Please write in the chat box. $90 plus 10 into 5. So it will be 140. Okay. And if you see 5 kilometer, what is the actual? Actual is also 140 and predicted is also 140. So can you appreciate that the predicted fare is equal to actual fare in this situation? Yes. Please write yes or no in the chat box. So Subha Priya is writing yes. Dr. Ayushi, Dr. Ajay, yes. So this is again a simple linear regression equation, which we have just made from this 5 data point. But like in biological world, that means when you have got a data set and many variables, then it is not so simple to get the value of A and B so easily. So we take the help of software to give these values for us. Now again, if I change the values of the data set in the previous example, like for one distance, it is 96. For 2, it is 112. For 3, it is 123. For 5, it is 170. Again, for 2, it is 106. So you can see the values are changing. For 2, one time it is 112 and the other time it is 106. So now it is difficult for me to make a formula without taking help of a software. It is difficult to find A and B. So in this case, if I take the help of a software, then it has given me 2 estimates. So this is the Jamovi output, which I have taken here. And it gives you in the form of like these 2 values. In the first column, it will write as a predictor. So predictor is like distance traveled in the kilometer. And this is the taxi fare, which is my dependent variable. This estimate 72.565, this is my intercept. That means this is my A. Remember, A was the intercept. And this is my B. B means coefficient. And right now, I'm not focusing on the standard error T and P. But with the help of this equation, can you predict the taxi fare for 5-kilometer distance traveled? You can take only up till 1 decimal point. So if you have to write equation, how will you write? Y is equal to, here the equation will be like 72 plus, means I'm taking the whole 72.5 and plus 18.7 into distance traveled. Means if it is X. So if you have to calculate, how will you do that? Please do that. $166. Okay, so everybody is there with the 166. So this was the equation which I have just written. And the actual fare is 166.5 or 160. That's okay. Yeah. So predicted actual is 170 if you see. And with the help of this equation, this 72.5 plus 18.8 into distance travel, your predictor fare is 166.5. Now, is there any difference between the actual and predicted? And if there is a difference, by how many rupees? So you all please write in the chat box. Actual fare was 170. With the help of equation, it was so 3.5. Subha Priya, Ajay, Farzana, Ayushi, Dr. Hilda Priya. Okay. So now, what is this name of, if I have to call it, this was the difference between actual and predicted. What is this 3.5? Yes? Can anyone write? What is the, yes. Dr. Farzana is right. Kirti is right. Priyanka is right. This is known as residual. And in this whole, rather you can say regression, that this, it works on this residual, and all the analysis which will be testing the assumption, the smaller this residual will be, the more accurate your model will be, isn't it? If like there's a difference of 1 rupee or 2 rupee, then I can say like, yes, my model is very good. But if the difference is very large, that means if the residual is very high, very large, then my model will not be a very good model, whatever I'm predicting. But again, since in one case, the previous one, there we have taken only one variable. But in this case, you can see if I take few more variables, like what is the traffic? If it is slow or it is very slow or smooth or very much congestion, whether it is a weekend or a weekdays, whether it is humid or pleasant or rainy, then if I take these variables, because you see, whenever you book Uber or Ola, you will see that if you book in the high rush time from 8 a.m. to 10 a.m., calculating the same, traveling the same distance will cost you more. Or if it is a rainy season, or if it is a festival time, then again, traveling the same distance will cost you more, because the other things are now into the interplay. There are more variables than only the distance. So that's how this equation becomes more complex when you consider more variables to predict an outcome, which is taxi fare in this case. Like here the taxi fare will be A, which is the intercept. And then there are other predictor variables also, like distance traveled, the situation of the traffic, whether it is a weekend or weekdays, how is the weather. And then you have got, like, instead of B, you have got like this B1, B2, B3. So there will be separate coefficient for each of these predictor variable. So if you have got more than one predictor variable, then this is known as the multiple linear regression. So simple linear regression, when you have got only single predictor variable. Multiple linear regression is when you have got more than one predictor variable. Again, can you find any relationship in this data set? Yes. So there are 10 cases, and in all these 10 cases, these are the data of 10 students. So they've got a percentage of attendance, and then they've got like marks obtained out of 100. So if you see, a 52% attendance is getting 68, 63% getting 77. Similarly, if you see the high percentage, let's say 80% here, 80%, then the marks is 94. So yes, can you write like what is the relationship between the attendance and the marks obtained? Can you show the chat? Positive. Yes. So there's a positive linear relation, because if one is increasing, attendance is increasing, marks is also increasing. Again, if I ask this question, can you find any relationship in this data set, like duration of exercise and fasting blood sugar? Yes, Subhapriya, you are right, like higher the attendance, more is the marks. In this case, what is the relationship in this data set? The second one. Here, if you see the duration of exercise, if it is 50 minutes, it is 96. But if it is like, if it is less, very less, 30, then the sugar is high. So this is a negative. Yes, right? Linear, we cannot say now, we'll have to see, but again, yes, there is a linear relation. There is a negative or positive that we can see. So based on these equations, we can predict the marks obtained by a student given their attendance, and we can predict the fasting blood sugar of a patient given their exercise duration per day. Now, we have added one more variable in the previous one. So in the duration of exercise, I have added gender also. So now you will see that we have got another variable, which is a male and female. So in this case, if you see male, even if like male is exercising for 50 minutes or 32 minutes, the gender and exercise are not related to each other. Why? Because female is exercising for 39 minutes also, and female is exercising for 55 minutes also. And again, in this data set, we can say that the gender has got, it is not related to this exercise duration. But in this case, if you see, like females are exercising for 50 minutes, females are for 32 minutes. And in each data set, you will see that females are exercising less, means like less than, you can say less than 40, because all the female values are like less than 40 and all the male values are like more than 40. So here the gender and exercise duration are related to each other. So that's why if you like just see the relationship between the exercise, the gender and the fasting blood sugar, you may say that, males are having less fasting sugar and females are having more fasting sugar. But when I have again taken one variable, which is the duration of exercise, then in this case, this is the confounder. Why this is a confounder? Because males are exercising more. So it is not because of gender they are having this fasting blood sugar, but they are exercising also. That's why you can see like this fasting blood sugar is less. So in case of this linear prediction model, you need to adjust for confounders also, and you need to see the interactions also. We'll see these two phenomena tomorrow, how you control for, how you see the interaction of the variable and how you control for the confounder. So now, till now we were predicting the values of a continuous outcome. So again, the closer this predictive value, the better is the equation. And we have said that this will be an accurate model. And if it is not very, close to residual, if the value of residual is very high, then we'll say that the model is not very accurate. So again, there's one question. If I wish to predict fasting blood sugar based on gender and duration of exercise, we recruited 10 person, asked their gender, the duration of exercise, and measured the fasting blood sugar. And data we have used to develop for the model of prediction. So which of the following best predict model theoretically? So they are the three models you can see, model 1, model 2, and model 3. So right now, please focus on model 1. So if you see model 1, before model 1, please focus on model 3. So what can you see in model 3? You see the actual fasting blood sugar and predicted fasting sugar. So what is the residual in case of model 3? Zero. So you can say it is a perfect model, means there is no residual. But actually, that is not true. Means it's not possible. Theoretically, you can say. If you focus on this model 1, then what is your comment on model 1? So there is a residual, 96, 100, 132, 128. But the residual amount of residual is small. It is like either 3 or it is 4 or it is 5. So that is the value of residual. This is model 1. But now if you see the model 2, what is your interpretation for model 2? Yes? Yeah, Subhapriya is saying 2 to 5, right? If you see the model 2, what is the difference? Difference is 2, like it is 96 actual, but predicted is 130. Actual is 132, but the predicted is 90. Okay. So yes, very high residual. It is not okay because either it is predicting less or it is predicting more. So that's why this model 2, if I make this model 2, this will not be accurate. Then I cannot say that, people will not use it in the case of evidence-based medicine because they will say that it is not behaving. It is going in a random way. So that's why you see that this is a ideal, but this is not a practical model. If you see the model 1, this is practically possible model. And if you see model 2, that is not acceptable at all because here the residuals are too high and again the direction is not fixed. So this this prediction, we use the linear regression, which is also known as the ordinary least square regression, OLS. It is known as the least square regression because we will see that I'll tell you why it is known as the least square, because the mathematical functioning of this equation, it is using this thing as a least square. So that's why it is known as the ordinary least square regression. So you will see many times it is like OLS. People call it as a OLS and OLS. There is a PLS also. So, but again, this OLS is ordinary least square regression. So what is this simple linear regression? Because it is known as simple because there is only one predictor variable. It is known as the linear because we try to fit the data in the form of a linear equation. And what is a linear equation? Y is equal to a plus bx. If it is a one predictor variable, if more, then again y is equal to a1 plus y is equal to a plus b1 x1, b2 x2, and that will keep on going depending on the number of predictor variable. So here the value of the outcome variable changes linearly with the predictor variable. And why it is known as it is regression? Because this whole data set we are trying to predict, we are trying to say it in the form of a linear relationship. That's why it is a regression. So what is a linear regression? It is a statistical tool which describes the relationship between a dependent variable and a independent variable, and it explains the impact of changes in the independent variable by the dependent variable, And again, there are terminology. What is the response variable? So dependent variable is known as the response variable, and the independent variable is known as the predictor variable, because it explains the dependent variable. That's why it is known as the independent variable. So now coming to this, just a few exercise or activity for all of you. So this X is a single continuous outcome variable, this Y is a single continuous outcome variable, and this X is a single continuous predictor variable. So if my question is, like, you have to predict BMI from observed abdominal circumference. So what is a predictor variable in this case, and what is a dependent variable or the outcome variable in this case? Yes, all of you please write down for the first objective. If the objective is predict BMI from observed abdominal circumference. Yes? So Dr. Carol is writing outcome is BMI. Yes, and abdominal circumference is predictor. Good. If the next one, like predict height of sons based on height of father. So what is my predictor? Okay. Yes, Farzana and Ajay, right? So Namrata is writing BMI outcome abdominal circumference. Okay. Outcome is son height, and the predictor is height of father. The next one, doses of medication and hours of relief. Yes, Priyanka, you are right. Predictor is father height. Okay. Dr. Arumal is writing predictor is height of son and outcome is no. Outcome is height of father. No, Dr. Arumal. Outcome is the height of son, because you have to predict the height of son. So the dependent variable is the height of son, and and predictor variable is height of father. In doses, medication, and hours of relief, relief is outcome, yes, and predictor is the dose of medication. And attendance and percentage of marks, Farzana is also written, like attendance is your predictor variable, and the marks is your dependent variable or the outcome variable. Yes. So in case of this objective, you have to perform this linear regression depending on the objective. So what is the dependent variable, and that you as a researcher are the best to judge. Any variable can be dependent or independent depending on your objective. So this again the same which you people have written, like abdominal circumference is the predictor variable and outcome is BMI. Height of father is the predictor variable and the outcome variable is the height of son. Dose of medication is the predictor variable, hours of relief is the dependent variable, and the attendance percentage is the predictor variable, and marks obtained is the outcome variable. Now coming to this again equation of a linear regression. So again, this till now we were knowing like y is equal to a plus bx, and if you like write it in the form of a linear regression equation, this y is equal to this beta 0. We call it as a beta 0. What is a beta 0? Beta 0 is your intercept. This beta 1 is your coefficient. This x is your independent variable. And then here in the equation, we have got this plus in the error or residuals. So these residuals are always there in the equation. The difference between the actual, this residual is there. So this model, if you see, these try to, it tries to form a line, and this line is the known as the fitted line, or this is the predicted value. And if you see the individual data point, so this is your individual data point or the actual data. This one. So there are many actual data here, and this is your fitted line. So distance between this actual and the fitted, this is known as the residual. So this is residual. This dash line, this is the residual. This is dash line is the residual. So residual, what is this? So this is your fitted. Fitted lines means it is the predicted. It draws a line. Using all the predicted values, it draws a line taking care that the distance from the original value or the actual value should be minimum. And software does it using the method of ordinary least square. That's why it is known as the ordinary least square regression. And in this case, generally on x-axis, you have got the independent variable, and on y-axis, you have got the dependent variable. So from this slide, we have learned few things. There's the x-axis, wherever you see these residual plot, the x-axis is always the predictor variable or the independent variable. The y-axis is always the dependent variable or the outcome variable. The line which you see in any equation, that is the line using the data point which is the predicted one. And the points which you see here, scattered here and there, those are what? Those are the actual values. Okay. So you should understand this, because when we'll see the plot, then we need to understand how the plot is look like, because you need to understand these basics to make us to check for the assumptions. That's why you need to know what are these blue points. Okay. So there are beta. So again, you are asking Dr. Manju, beta 0. So beta 0 is an intercept. It is a constant actually. So we define beta 0 when all these independent variable is 0. So when this is 0, this is 0, then you say that the value of y at all, when all the independent variable is 0, then the beta 0 is the value of y. So it's an intercept, it's a mathematical this thing. To fit into a regression line, this intercept is needed. Many times it will make a sense to you, many times it might not make sense to you when you see the equation. We'll come to this intercept again. And since it takes the values from the data, so this intercept is a constant. So this beta 0 is a constant, because you will see there is no predictor variable associated with it. This is a constant. So you define it when there are these, when these are 0, then when your independent variable, like the levels, if it is a categorical variable, so the reference category that it takes as a 0. So those reference category, and if it is a continuous variable, then at the 0. But actually for continuous variable, it doesn't make sense. Why? Because like if age is a continuous variable, and if you say at age 0, so but age 0, if you have not taken that into your data, this will not make any sense. Okay. But again, for theoretical concept, this intercept is needed, because without that intercept, it will not form a linear equation, and it will not give you a line, because this equation which you are seeing here, using this equation, it gives you this line. Okay, this fitted line using this equation. And this is using the method of least square. Least square means it sees the value of the residual and see where is the residual minimum, and then it plots this line. That's why this method is known as the ordinary least square regression. Okay, have you understood this up till this point? Am I making sense to all of you?
Madam, can you please repeat this blue lines?
Okay, I'll again repeat. Blue lines, so there's you are saying this dotted one?
Yes,
Because
ma'am.
okay, so for blue line, I'll again come to the blue line, Subhapriya. Just after this slide, there is an exercise. Actually, these lines represents the value of residual. I'll tell you. No, not taxi one. Subhapriya, I'm coming to your question in like after 3-4 minutes. Apart from that, any other person who wants to understand anything else or any other concepts? Okay. Okay, so Dr. Shamsad is saying taxi one. Okay, so Subhapriya, you can see like those difference in residual. Remember, when you calculated the taxi fare for 5 kilometer, your predicted one was 166. Remember? 166.5. And your actual was what? 170. So this dash line, it represents that difference of 3.5.
Okay, ma'am. Okay.
Okay, because if you see like, okay, I'll explain here also. If you see this line, you have to see the value of y. So since y-axis is your dependent variable, you draw a line here and you see the value here. So this is your fitted one, means the predicted one. And this is your actual. So the difference between this actual and predicted, this is this dash line, and this is the residual. So actually, this dash is a residual. Whatever dash blue is, you can see it. So this you will see a very less of residual. But here, if you see this value, the amount of residual is very high. Can you see?
Yes.
This much is the amount of residual. Whereas in this case, if you see, it is very less. Only this much distance. If you like just draw, take this to y-axis, these two, only this small distance is the residual.
Okay, ma'am.
But again, I'll explain this once again. So what are the underlying assumptions? So underlying assumptions are for this linear regression. And if you want your model or your prediction equation to be very accurate, you please check for these assumptions. You might say that you have seen like nobody checks it. And if you read the linear regression equation, many time in the manuscript, they don't report probably, even if they have checked, because we cannot say that they have not checked, but they don't report. But the main aim is please do report, because once you report, then only the audience will, or the reader will come to know that you have actually tested it. So assumptions are very important, and you should report all the assumptions. You should report all the assumptions, met or not met. If not met, then what did you do? And if met, generally for the first time, we'll assume that all the assumptions are met. So there's one dependent variable which should be continuous. The independent variable can be continuous or categorical, but for demo purpose, we have taken the independent variable also as a continuous. There should be linear relationship between the two variables, and there should not be a significant outlier. And in case of this be significant outlier, we check with the help of a Cook's distance. I'll tell you what is a Cook's distance. Because in SPSS, it is by the case-wise diagnostic, but here it is the Cook's distance. And because in case of a normal descriptive, generally what we use, which you people have written, box and whisker plot. But in case of a regression, there's another statistical objective concept which is known as the Cook's distance. And we use that Cook's distance to label something as a significant outlier. And there should be independence of observation, which we check using Durbin-Watson statistics. And then data needs to show the homoscedasticity. And we'll see what is this homoscedasticity. These are the assumptions of a simple linear regression. That means here only a predictor variable is only one variable. Once we understand this, then we'll add more variables in the equation. So we'll see these one by one. What are these assumptions? So before we go to these assumptions, I think should we give them a 5 minutes? So we were, what is okay? We are checking for the assumptions now. So the first assumption is that your predictor variable, there should be a linear relationship between the predictor variable and the like outcome variable or the dependent variable. So how to check for the linear relationship? Generally, you check the residual plot, and if the direction, in this case, you can see this graph, and there is a line. So you can see like if the one variable is increasing, and these are the two variables. So exercise duration, if you see this x-axis, this is the exercise duration, and the y-axis is the fasting blood sugar. So if the exercise duration is increasing, the fasting blood sugar is decreasing. That's how you can see this scatter plot is like this, and you can see say that there's a linear relationship. Because this is a linear regression, so both the dependent and independent variable should have a linear relationship. These are few examples of scatter plot where you can see a non-linear or a linear. So in this case, you can see the lines here, it is like a linear line. If you see this is a non-linear because this is like a hyperbola. This is again like an inverse U. So this is not a non-linear. So in such case, you will have to go for quadratic or segmental regression or some other form of regression. In these two, you cannot perform linear regression. Here you cannot perform, and in this case, you cannot perform. Then some other type of equation, like there are other types of regression equations also, like segmental or the polynomial regression, that you can go. But for linear regression, because it is, again, remember, it is in the form of y is equal to a plus bx. So for that to be like applicable, you should go for this scatter plot. When the scatter plot is something like this, then you can perform a linear regression. Now again, coming to that Subhapriya question which she was asking at that time, I tried to explain it partially, but again fully I am explaining it here. What is a residual and what are the meaning of those dashed line or the line which you can see here. So again, if you see this is the plot of residual plot of BMI and cholesterol. And BMI, I have taken it on the x-axis. So BMI is my x and x is your predictor variable. And this cholesterol is my dependent variable. So this dependent variable or the outcome variable. And what are these points? What are these individual points? Yes, all of you, please type in the chat box. What are these blue dots, which you can see here in this plot? Individual data. It is the observed value. Very right. It is the observed value. And these lines are the predicted one. Okay. So now how you will calculate the value of residual? So let's say I've given you the example with the two example. One is the this 91 number patient ID. If you see this 91, and the other is this case number 2, this one. Yes, you are right, Farzana, observed and expected. This is the same. Here, instead of expected, we call it as a predicted. So actual and predicted. So this one, if you see this 91, what is the actual value? So actual value of this 91 data, we have to see the value on the y-axis. So it is like 7, I have not correctly drawn it, but observed value is 7.89. And if you see the predicted value, so predicted value is this one. The distance on this predicted or the fitted line, if you drop a 90 degree, on the 90 degree angle, drop a line and then see its value. So I'll see the value over the x, this y-axis. So on y-axis, it is approximately 5.79. So the predicted value is 5.79. So this distance, the distance between these two is the residual. So the residual is 2.18 in this case. And this is your unstandardized residual, means it is the raw residual. You can say raw or unstandardized. Remember, in case of a chi-square also, we have understood the concept of unstandardized versus standardized. Here also there's a concept of unstandardized and standardized. So unstandardized means it is the raw residual, the difference between the predicted and actual. Again, if you see this data point, so this, if you see the actual value, actual it is like 4.8 actual value. And if you see the predicted one, predicted, you have to draw a line from this fitted line. So I have drawn a line on the y-axis. So this is like 5.35 is my predicted one. So here now it is in the negative direction. Why? Because what I'll do, observed minus predicted. That's how, like in the chi-square we write now observed minus expected. Here we write observed minus predicted. So the value is in negative. So that's why you will see that there are many values which are, whatever value it is in the below this line, this is in the negative direction, and whatever lines are above this line, this is in the positive direction, because this will be your positive value and this will be your negative value. So these are the errors or residual. So have you understood, Dr. Subapriya? You have understood at that time point also, but
Yes, ma'am. Yes, ma'am.
okay. So these lines, whatever here in this part, they have not drawn the line. But if you have seen this one, there they have shown this. In actually, when you plot it, that line will not be visible. This line, it has been drawn like this, but generally, if you see the plot, because there are so many data points that if they draw the line, then it will be very messy, that graph. So that's why those lines you will not see. So now this was your unstandardized residual. So similarly, residual, you standardize it also. So there are basically three type of residual. So one is the ordinary residual, which is also known as the unstandardized or the raw residual. There is something known as the standardized residual. So what is the standardized residual? If you divide the ordinary residual by the population standard deviation, it is known as the standardized residual. And then there is something as the studentized residual. So what is a studentized residual? If you calculate the standard error of residual, and if you divide the raw residual by standard error of residual, then it is known as the studentized residual. Okay, so these are the three types of residual. In SPSS, if you see, generally all the analysis we perform in the studentized residual. But here in JAMO, if you see, generally it is performed on the standardized residual.
Ma'am, shall I
Now,
ask a doubt?
yeah, sure.
Ma'am, why do we need to standardize? Like, why can't we leave it like ordinary residual?
Okay, again, remember, wherever we are using the term standardized, that means you want to compare. Because if in an independent variable, there will be many residuals now. Like residual, there will be many predicted variable. One BMI is there, then another maybe heart rate, then another maybe the creatinine value. Every has got a different unit. So that's why if you standardize it, then you can do the comparison. So that's why wherever we call it as a standardized, then even if there are different units and different predictor variable, then you club it all together and then you can compare it. That's why we always standardized these. Generally, all these graph which you see plot, that is performed on the standardized residual.
Okay, ma'am.
So now coming to the this residual, the second assumption. So that was my first assumption. So first assumption was like these are the two assumptions, like there should be one dependent and one independent variable. There should be linear relationship between the two variable. And then this linearity, these three I'll see, and then it comes the next one, which is like a residual should have a normal distribution. So like if these are the residuals, and you plot this thing, if you see this plot also, this is again on the y-axis, we have taken the standardized residual, and in x-axis you have got this one. So if you see, we'll see this in JAMOV, but it should be like we have seen that QQ plot. So QQ plot is again here, and it should be along this diagonal line. So you know the interpretation of QQ plot. So you plot it, and generally that plot is there as output. You have to interpret it. Now the third assumption is like the data needs to show the homoscedasticity. Now, what is a homoscedasticity? So I'll come on this homoscedasticity. So variance, if you can recall the concept of variance, we have understood the concept of variance in case of a independent sample t-test. Remember what test we used to perform to understand or to check for the homogeneity of variance? Yes, all of you please type in the chat box. In case of a independent sample t-test, what test do we perform? Yes, Levine's test. Very right. So in case of ANOVA also we used to do the Levine's test of homogeneity of variance. Here in case of a regression, again we are checking this homogeneity of variance, but here the concept is known as the homoscedasticity. So if I break the term, we'll see what is homo. Homo means like same, and scedasticity means like variance or the spread. So again, in regression, what is the concept of variance? So again, if you see the mean, this example, these two. So mean of these two, if I take these two people. So one person has got a height of 127 and another has got a height of 140 centimeter. So if you take the mean is 130. Again, these are the two people having 130 centimeter height. So again, the mean or the average is 130. So by mean, you cannot come to know regarding the dispersion of the data. And variance is something where it tells you about the dispersion of the data. So if your model is accurate, then the variance should be homogeneous across that data point. If the variance is not homogeneous, then your model will not be accurate. So that's what we call it as a concept of homoscedasticity. So like if I see these two averages, then can I say that average of height is equal in both the sample? Can I say that? Yes or no?
Yes, ma'am.
Okay.
Average is yes.
Yeah, but can I say that the variance of the height is equal in both the group? Can I say that? Because in first case it is 120 and 140, in the second case it is 130 and 130. So I cannot say about the variance because variance is not here. There is no variance. In the second case, there is no variance because both the person has got the same height. So there's no variation. But in the first case, although the mean is same, but there is a variation. So the sample variance is in the second case, it will be 0. And if I have to calculate the sample variance of this case, so how do we calculate variance? So remember, variance is always the sum of square. And sum of square is like you calculate the distance from the mean, you square it, and then you divide it by the sample minus 1. So here, if I calculate mean is 130, so I will like 140 minus 130, it will be plus 10. And here it is like 120 minus 130 is in the minus 10. So here I square it. So if I square it, it will be like 100 and 100. So 200 divided by 2, so it will be 100. So the variance in this case is the 100. So for height, we can easily appreciate variance. But if there are many variables, so like in this case, there's only one variable. But in case of a linear regression, if it is a simple, you take one. But if it is a many, like a variable, predictor variable, like let's say if I have to tell about the cholesterol, so SBP, BMI, TSH, all the variances, if the variance I calculate independently, then how will I take the account of all the variables together? For example, see, this is one data set where in the first column it is the gender. So there is a male and female, and it is the TSH level. So TSH level is 11, mean TSH level. And this is the data set 2. In the second data set, the TSH level, individual TSH level are here, and the mean is 11. So if I ask like which data set has got more variance, what will be your answer? Yes, data set A or data set B. So variance is more in the second data set. Yes, because you can see it is varying from like 4 to 18. And in this case, it is varying from 9 to 14. So variance is more in the second data set. So what is a variance? So basically a variance in statistics, it measures how the values in the individual data set, how far they are from the mean, and it gives a idea about the dispersion. So if you see that this data and this data, these two picture, this first one, this one, and this one. So by picture only, by seeing only, which will have more variance. If this is A and if this is B, so which has got more variance, A or B? B, yes. So by seeing the spread, so if the values are spread out, dispersed, then it is the more variance. If values are less, and this red point is the mean. If you see this red dot, this is the mean. So from the mean, if the values are very close, then this is having less variance. If from the mean the values are very much spread out, then the variance is more. So generally, if you see, there is a two type of variance. There is a sample variance and there is a population variance. So generally, we use the population variance in case of a calculation of a linear regression. I will not tell because that's not needed. Now, we in case of this linear regression, we understand like the dependent variable and in the independent variable, and we have seen like in R square. What is this R square? So basically, this R square also tells you that variance explained means the variation in the dependent variable, how much percentage of independent variable, by which percentage from one person to another person, you can see like the variance of those dependent variable was being explained. So like let's consider this example. If I'm investigating the influence of like health factors on cholesterol. So cholesterol here is my, if you see the this variable, so cholesterol is my dependent variable. And there are many independent variable like age, weight, exercise hours, blood pressure reading. And I have to see all these variables, how it is collectively influencing the individual cholesterol level. So suppose I have got these 8 people in my study and I analyze the cholesterol level in 8 individual, each having a distinct age, weight, exercise, like how much exercise they are doing, and the blood pressure. But again, then there is something which is known as like variance. So why it is varying between all these people? Yes, you will see like many of us, this is a very common question. Even if there are many factors in COVID, only you must have experienced that everybody did not get COVID because like there was a gender, there was a pre-morbid condition, there was exposure to the people who are already having COVID, or there were people who are having previous pulmonary disease or lung disease or any other comorbidity, but everybody did not get the disease. So because there are many factors, so if you see what is this variance? So this variance is again the same thing. Like even there are people who have got a distinct weight, exercise, age, and blood pressure. You will see that the cholesterol values that was differing between people. And if I want to know the reason behind it, like why the value of cholesterol is different in all these people, then even if the exercise or weight or age is nearly same, in spite of that you will see that there might be some variations. So this variance is we are trying to understand. So this variance we are talking in terms of a dependent variable, the predicted value or the value of the dependent variable, why there is a variation in the dependent variable, and what are the factors means what are the individual variable which is affecting this is the variation. So now the next question is why this variation occurs. So basically whenever there is an interrelationship, so all these variables like socio-demographic, lifestyle, or like exercise hours or pre-existing illness or genetics, they are interacting with each other. So certain variables are more playing a more heavy role or pivotal role in this variation, like age, weight, exercise duration, and blood pressure. So probably I have taken those variables. So again, like if I have taken this age, weight, exercise, and an SBP, and my dependent variable in this case is the cholesterol. Okay. So now how I will calculate the variance? So we separately estimate the R and R square for each variable. So if you see age and cholesterol, the R square is, so I have performed the simple linear regression for all these factors individually. So with age and cholesterol, it is the R square is 95, means R square is 91%. Weight and cholesterol, the R square is 93%. The exercise duration and the cholesterol is the 35%. And systolic blood pressure and cholesterol is 84%. Okay. So can I add all these variances together to contribute 303% variance in cholesterol level? If I say this statement, am I correct or I'm incorrect? Am I making sense to all of you? Okay, so Kirti, you are answering no for this variance, or I'm not making sense? I don't know. No is for what? Okay, variance. Thank you, Kirti. And not correct. Ayushi is writing. Geeta is writing no. So I cannot correct it. Yeah. Why? Because when these variables, they are acting together, means all the variables are acting together, then I cannot add these variances. And in that case, because there is an overlap. So these 303% variance is possible only if there is a no overlap. But generally there is overlap because in one person, the age, weight, exercise, and SBP, all these four are acting together. So that's why we call like and that's why we check these variances with the this thing known as the heteroscedasticity or the concept of homoscedasticity. If this assumption is met, we say that yes, homoscedasticity is met. If not met, then we say that the data is heteroscedastic. So this was the variance concept of a linear regression. So this is a little different from the variances which we have done in case of a independent sample t-test and ANOVA. Here, generally, because here it is not the one variable. In ANOVA or in one-way ANOVA or in independent sample t-test, we were only seeing like if I am measuring the SBP in male and female. So there was only one variable. I'm not like predicting something. So in that case, the variance was different. But here, if there are many variables and they are acting together, then the concept of variance that we calculate using residual and that a residual plot that we'll see. So this is the variance in case of a linear regression. Now so we have seen underlying assumptions of the dependent variable being continuous. Independent variable can be continuous or categorical. There should be linear relationship between the two variables. How do we check for it? Again, we check it with the help of a residual plot. The data needs to show homoscedasticity. That again, we check with the residual plot. I'll demonstrate all these concepts on the data set. And then there should be independence of observation. So what is this independence of observation? And this outlier, again, by mistake, everywhere I have written this case-wise, but this is in case of a SPSS. This doesn't give you case-wise diagnostic. Instead, it gives you Cook's distance. Now coming to independence of observation. So what is independence of observation? This independence of observation, you know that the data, the residuals, which are there, they should not be correlated with each other. So correlated, what do you mean by correlated? Again, this is a study design issue. Generally, we say that it is a study design issue, and this is again, we also call it as an autocorrelation. So what is autocorrelation? Okay, this again, so no, before that, I think the slides are of homoscedasticity. I have not explained it fully. So this homoscedasticity, it is also known as the homogeneity of variance. Homo means like equal and scedasticity means spread. So how do we measure it? If you see this graph, if you draw a line, it is like scattered. It is not showing any pattern. But if you see these residuals, these two, so here you can see there's a fanning out. Let me. If you see this point, so here you can see like there is there is no pattern. Pattern means if you draw a line, imaginary line, then the spread of residual here and here, it is almost same. Means it is not making any pattern. But if you see this, there's a fanning out. Here the residuals are very close to the fitted one, and here the actual ones are very far from the fitted line. So it is making a pattern of a fan, or we call it as a fanning. So here the homoscedasticity assumption is met, but here the homoscedasticity assumption is not met. Okay. That means, what do I mean by this is a residual plot? So you understand this by the visual inspection of a residual plot. If you can find out any pattern, then the homoscedasticity assumption is not met. If you are finding a pattern like a fanning out like this, or a funneling in or a funneling out, then the homoscedasticity assumption is not met. So here there is no objective way. Like in case of a Levine's test of equality of variance, what we used to say, that if the p-value is more than 0.5, then the homogeneity of variance assumption is met. Remember how we used to test the homogeneity of variance? Yes? Can I have like any response from your end? Can you recall the homogeneity of variance concept in independent sample t-test and the ANOVA? Anyone? Where we used to test it with the help of a Levine's test of equality of variance, and it was an objective way. Objective, what do I mean by objective? Means if I say that the p-value is more than 0.05, then the homogeneity variance concept was met. This assumption was met. But in this case, in case of a linear regression, there's no objective way. It doesn't give you a p-value. Rather, by the visual inspection of scatter plot, by this visual inspection of the residual plot, you have to make out whether the assumption of homoscedasticity was met or not met. So how do we make out? If there's no pattern. So in the first case, it is having a constant variance of error or residual at all level of independent variable. Okay, that means if you see the distance will be same across this line. Same means the variances of these points are same. If I draw a line, then if you see the distances of these individual points, they are approximately like similar across the line. But if you see this, here the spread is less and here the spread is more. So I will say that the residual variances are not same across all values. Okay. So in simpler terms, the homoscedasticity means that the spread of the residual around the regression line is roughly the same across the entire range of predictor values. Am I making sense to you? Like in this case, if you see, just a second. This one, the first one, here the concept of homoscedasticity, this assumption is met. But in this case, it is not met. Why? Because if I draw a line, rough line, you see that here the spread is more and here the spread is less. So variances of all observation across the all values of independent variable are not the same. So that I mean by the assumption of homoscedasticity. Here again, if I ask this question, is residual here homoscedastic or the heteroscedastic? What will be your answer? Please write. Yes. Homo. Okay, true. Again, in this case, homoscedastic or heteroscedastic? Someone is writing homo, someone is writing hetero. If you see the spread is less here, but spread is more here. Similarly, here the spread is more. So it is making a pattern. And that's why if you see the SPSS and LERD, they say that fanning out. So this is like an inverted fan. And this is like a everted fan. So if it makes any pattern like this or funnel, they call it as a fanning or funneling. If such pattern you see on the residual plot, that means the variances are not constant across all values of the predicted one, and that's why then you cannot perform a linear regression. If this assumption is not met, then your data is not fit for linear regression. Am I making sense to all of you?
Yes, ma'am.
Okay, thank you. So how to remember? So if I say that homogeneous means in uniform or identical, whereas heterogeneous means it is different. So concept of homoscedasticity, remember, if it is homo, that means it is uniform. The variances are uniform. It is hetero, that means the variances are not uniform. So now again one question, why this heteroscedasticity? Why this heteroscedasticity occurs? Because models, in models you have got a large number of data. Data set is generally 100, 200, 300, right? So if in your model, if there are large number of data, then you can say that it will show more variance. If I see this data and I'm trying to model the number of patients coming to the AIMS Patna in the last 10 years, then there will be a lot of variance. Why? Initially, when there were less services, the number of patients were less. But when there are more services are getting added, then of course the number of patients are large. So depending on how your dependent variable is behaving, that again decides about the variances or the concept of homo or heteroscedasticity. So in a model, when you have got a wider range of observed values, those sort of data set or models are more prone for heteroscedasticity. So how do you fix this heteroscedasticity? So I said that if your model or if your data set is not fulfilling the assumption of homoscedasticity, then you cannot perform this OLS or the linear regression. In that case, you have to go by the weighted, there is a concept known as the weighted ordinary least square regression that you have to do, which we are not covering here in this session. Or you can transform your dependent variable. So transformation, you can do the log transformation, or there are other transformations also. So you have to transform the dependent variable if the assumption of homoscedasticity is not met. So now again with this, let's understand this with some more example. So let's consider this data set where I want to predict the individual lung capacity based on their age and BMI. And but again, I have introduced this concept of heteroscedasticity to demonstrate this. So this is a data set. I think we have got the data also. I'll show on that data. So this is the age and BMI. These are the two independent predictor, and I have got this lung capacity. So these are the values. So I'll go with this data. So now I'll start demonstrating simultaneously. Why? Because then again, at the last, it will be difficult for you people to understand. So simultaneously, I'll be showing you. So if I come to this data set. No, this homo and heteroscedasticity, that's a data set is where?
Presentation में conceptual data set.
Okay, so this is like data for heteroscedasticity and homoscedasticity. So all of you are Familiar with the Jamovi interface? So this is the Jamovi and version which we have used. Let me delete this. So how to delete? You copy it like all and then remove. So all analysis is removed. So this is the Jamovi. I think most of you are familiar. This is a dynamic interface. If you like perform any analysis and if you move the variable back to the window, the analysis will disappear. We'll just see this. So let's say now I have to go with this regression. So how to check with this? Click on this regression. In the basic statistics, we have learned regarding the frequencies, the t-test and exploration. ANOVA. These options we have seen in the basic one. We have seen the frequencies. All the chi-square comes with this option. ANOVA, we have learned the one-way ANOVA. We have also learned the t-test, paired t-test, independent sample t-test. And in exploration, you have got the this thing, descriptive statistics. For regression, you have to click on the regression and I'll go with this linear regression. So if you go to linear regression, my dependent variable was, if I see, systolic BP. So I'll move this here. Systolic BP is my dependent variable. And my two independent variable are the age and stress level. So I will move this to covariate. So in this box, you have to move the continuous variable. And in this box, you have to move the categorical variable. So how to check? If I have to check for assumptions, I'll go for this assumption. And I'll check for this. Let's first see the residual plot. So I'll see the residual plot. So how this residual plot are like made? So if you see, the first plot will be a plot of residual versus fitted. So what is a fitted? Fitted is a predicted one. So it makes a plot with the x-axis, the predicted one, and y-axis is the residual. And this is the, in the case of a residual, remember this 0 starts from here. Generally, what happens? Like here you take it as a 0. But in case of a residual, this 0 is here. So if you have to see the variance, so can you appreciate that the variances are approximately same? If I come to this, it is not making any pattern. You have to see this one. So you can say that it is homoscedastic. Data is homo, it is showing the homoscedasticity. Now, I'm not showing the other thing. I'm only showing you the graph now, the residual plot. Now, if I open another data set, heteroscedasticity. So again, how I'll do? This is the same systolic. I have to predict the systolic blood pressure. So I will remove this analysis. Again, the same systolic BP and stress level. And if you go down and click on assumption check and click on this residual plot. So now you can see that there's a fanning out. If you see this, if you take a line, then again the distances are not same. There's a fanning out. You can see there are few residuals here. The distances of residuals are not same. So that means like the data is heteroscedastic. Now coming to these are the plots which I wanted to tell you. So if you see this, basically there are 3 types of plots. So the first plot, in case of a residual plot, so we use this residual plot to check for the linearity assumptions also and to check for the homoscedastic assumptions also. So there are 3 types of residual plot. The first residual plot is between the residuals and the predicted fitted value. And what do I mean by fitted value? Fitted means the predicted value. Then the second, there are other residual plots between the individual predictor and the residual. So the two predictors here are the age and stress level and the systolic BP. So one, it makes with the systolic BP the actual one and the residual, and then other one like age and residual, and then the third one with the stress level and residual. So depending on the number of variables, it makes those many residual plot, right? So basically we see this residual plot, this one, the first one, the fitted and residual. So the same, I am explaining it here. The residual plot basically. So in the residual plot, it on the x-axis, it gives you the fitted value. So what was the fitted value? Fitted value of the predicted SPP. And on the y-axis, it was the residual. And residual is what? Actual minus predicted. So purpose is, again, it checks for the linear. Like I said, with this graph, you can check for the linear assumption, whether they are two of them are linearly associated with each other. And it checks for the homo or heteroscedasticity. And then the second residual plot was on the x-axis, you take the actual blood pressure, and on y-axis, you take the residual. No, it gives you. And again, it should ideally resemble a random cloud, because I said that it should not make any pattern. And then the other two are with the independent variable, like stress level, and with the other two, like it was the age. So it checks whether the residual, whether it correlate with any predictor. And again, it will tell you regarding the relationship. So again, I said that if there is a violation of homoscedasticity, either you can perform a weighted least square regression, or you can do a log transformation of the dependent variable, or what you can do, I'll tell you what are those influential points or outlier. You can check for the outlier, and you can try, after removing the outlier, you can perform the linear regression, or you can perform a non-linear model. What is a non-linear? Means those are the segmental or quadratic linear regression. Those are not the linear model. So that means that the relationship is not linear. So you cannot go with the linear regression equation. Again, I said that in residual plot, if you see this residual plot, the x-axis does not start from 0. If you go to JAMOV, and if you see the value here, it starts from this 120. Here it is not 0. Why it is so? Not 120, like it will be something like 112 or something like that, because it takes the values which are there in your data. So that's why it doesn't start from 0. So I think this was one question I think few participants, they asked in our previous workshops. Because in residual plot, why the x-axis or the predictor variable does not start from 0? Because basically here you check for, like, whatever the data point is there. In case of your linear regression model, it takes that data point. So actually, practical range of the data, it does not start from 0, because there is no value of SBP in my data set that is 0. That's why the SBP does not start from 0. Now coming to the regression and the anomalous data point, because I was talking about the outliers and about there is another concept which is known as the leverage point. And I was talking about the Cook's distance. So they are all related to how the individual data point, it is influencing your regression model. So we'll understand this concept now. What is the outlier? What is a high leverage point? And what is a Cook's distance? So are you guys with me up till this point? Or any concepts you have not understood? Then we may repeat it. Otherwise, I'll go few more assumptions. So till now, we are only on assumptions, okay? So we have tested for the homo or the heteroscedasticity. We have seen the assumption of linearity. And with this only, we will see the assumption of normality. The option of QQ plot is there. And we have seen the assumption that the dependent variable should be continuous. Independent can be continuous or it can be categorical. So these 4 assumptions we have tested. Now I have to see if there are any influential data point or outlier and high leverage. So what are these concepts? We are going to understand now. So yes, complete silence. So can someone guide me? Am I making myself clear to you people, or are you people taking it as a heavy session? Priyanka said yes. Farzana said yes. Okay. So I am moving. Probably if you like do it, once we'll do it now. Right now, I'm telling you all theoretical. In between, I'm doing few like hands-on, but these theoretical background is needed. Otherwise, in a software, if you put the data, it will give you something. But it is you who have to decide that whether you can go ahead with the model or not. The Jamovi cannot decide. That's why it is important for you to understand. Now, what are these 3 concepts which we will see? So the first concept is the outlier. What is the outlier? So outlier is a value of y. So what is a y? Y is my dependent variable. So it is a data point that has got a large residual. And what is a residual? Residual is the difference between the observed and the predicted. So remember the 2 which we have seen, the 91 in this, there was a one graph now where I explained. Let me go back to that. Yes, can you recall this one? This 91 set. So 91 here is the outlier because it is away from all this data point. Okay. The value of residual was very high here. So that's why you can call it as an outlier. Okay. So what is an outlier? If the value of residual is very high for that particular data point, that is an outlier. So outlier is any data point that has got a large residual. And what do I mean by residual? Residual means the difference between the actual and the predicted. And it is visible on the residual plot. It will be far above or below than the rest of the term. But if you see, if a particular data is only an outlier, it distorts the regression line and the error terms are also inflated and it affects your model fit. But again, it does so only if it has got a high leverage. Now, what do we mean by high leverage? So again, this is outlier. You can see in this point, this is an outlier where this has got a very large residual. But if you see the shift in line, this dotted is the line. This one is the line the regression line. So this is outlier. Again, coming to high leverage. What is a high leverage? So high leverage is again, it is a data point with the unusual value of x. X means what? X here is the independent variable. So the first one, the outlier, that was more with the value of y, means the predicted and actual. But high leverage is the point related to x. That means if you have got a high value or a very high different outlier value of an independent variable x, then it is known as the leverage point. So in multiple regression, how this leverage is calculated. So I'm not going into the statistical concept how it is calculated, but you should remember that it is related to the independent variable. So high leverage is a point, it pulls the regression line towards themselves, especially if they are also outlier. Means a point which is outlier and which is a high leverage, then it shifts the regression line. For example, if I'm predicting the blood pressure from age, so age is my independent variable and blood pressure is my dependent variable. So if I've got this data point of age like 30, 35, 40, but there is one person in my data point who is of 100 years. So 100 years, of course, it will have a 160 or very high BP if there is a linear relationship between these two. So this 160 is a high leverage because at this high value of independent variable, I'm seeing this value of dependent variable. So this has got a high leverage. So if this high leverage is this outlier also, then these two together, we calculate it in the form of a Cook's distance. So what is a Cook's distance? So basically Cook's distance combines the leverage value and the outlier into a single measure to identify influential point. So any point that has got a Cook's value of more than 1, it will potentially influence your model, and that should be removed before you perform the regression analysis. So let's see how we do it. So I'll go to the same data set. So there's a one data which is for the Cook's distance. So suppose my predictor variable is the systolic blood pressure. So I'll move this systolic, or let's say it is cholesterol level, and my predictor variable is the SBP, exercise hours, age. I'll move all these, and stress level here in the factor. And then I'll go to this assumption check. And in assumption check, you can see there's a Cook's distance. So it gives you the overall Cook's distance also. So if you see the overall Cook's distance, it is 1.45. But if you see the individual, it doesn't give you the, if you come to this save option, and if you click on this Cook's distance, and if you go to this data, it will give you the Cook's distance. So can you see the Cook's distance here? It is all are less than 1, except this one. It has got a value of 27. Can you see this 27? This one. So this is if the Cook's distance is more than 1, I need not to include this data point in my regression analysis. Okay. Am I making sense to all of you regarding this Cook's distance? So there are 3 it should be less than 1. It should be less than 1. Cook's distance should be less than 1. And that's why because of that here you will see that it has dragged the mean also towards 1.45. If I delete this data, let's say, if I delete this, okay.
आपको कोई कोलेस्ट्रॉल वैल्यू दिखेगा ना
If I delete this cholesterol,
कोई वैल्यू
so now you can see the mean from 1.45, it has come 2.08. Okay, so the Cook's distance should be less than 1. So by individually seeing the data point, you need to decide if the overall Cook's distance is more than 1, that gives you like a hint that there will be individual data point where the Cook's distance, where some of the data point is showing more than 1, the Cook's distance. Okay. So what is a Cook's distance? Basically, the Cook's distance takes into account of both the concepts. And what are those concepts? The first one was an outlier. What is an outlier? Outlier is a value which has got a high residual. That is outlier. And what is a high leverage? High leverage is that in your data point, if there is any independent variable, which has got a high value, which is different from all other variable, then that is known as the high leverage point. So if a data point which has got a high residual and a high leverage also, these two gets combined into a single unit, which is calculated statistically on GEMOV, which is known as the Cook's distance. So any data point more than one showing the Cook's distance should be removed from the analysis. Or if the overall Cook's distance also, if it is more than one, then you need to check for the individual data point and delete it before we go for the model building. So, am I making myself clear to all of you? What is a Cook's distance? What is a high leverage point? What is an outlier? Yes, can I see the chart? Yes, Ajay has written yes, Dr. Hilda has written yes. Okay. So if it is yes, but still it takes time to remember. I understand. Even if we keep, like we don't do, we tend to forget, especially the values. So never mind. You need to understand the concept. The factual thing you may forget, but the concepts you should remember. And if you like do it once, twice, or thrice, then it will be clear. The more you do, the more you will remember. I know it is difficult. And in linear regression, you will see there is a lot in the assumption section. Why? Because you are predicting something. And if your data set is not following those assumptions are not getting fitted to your data set, whatever you will predict, the standard error, your coefficients, those will not be correct. So you will be, concluding a wrong prediction on a wrong model. That's why it is important to check for each and every assumption in case of a linear regression, or for that matter, any model making, whether it is linear or logistic or it is Cox proportional. So I'm not telling you the distance. So Cook's distance is, again, it is a high influence observation, which is both a outlier and it has got a high leverage. Because if you see independently, the outlier and leverage that do not move the regression line. But any data point which is both a high leverage and a high outlier, means outlier, that moves, that together is known as the high influence. And high influence is measured in the form of a Cook's distance. Okay. So high leverage and outlier together makes high influence, and high influence is measured in the form of a Cook's distance. If the distance is more than 1, your data is unfit for regression. So that's what I have just concluded, that high leverage is driven by the independent variable and outlier is driven by the dependent variable, and Cook's distance takes both these variables into account. Okay, now coming to the estimated, I'll explain the estimated marginal mean later. First, any other assumption? I'll again come, don't worry. Let me check what are the other, or let me explain. I think I can go for the demo. I'll explain the marginal means also. If you see here, this is the data.
Yeah, but I think
That's what I'm not explaining.
That's article discussion.
Okay, so now I'll start the demonstration part. So this was a reference article which we have shared. So all of you have gone through this. I've deliberately not tested few of the assumptions. I'll tell you while we are analyzing the data. So Dr. Namrata is writing yes, but so it is. It was an article of like they have performed a multiple regression model to analyze the total length of stay for patients undergoing the laparoscopic appendectomy. So how they have done it? Can someone read this? These two parts. Can someone read this? If someone has not read, yes. Yeah. Any volunteer?
Yes, ma'am, I will. Go ahead, Ajay Kumar, go ahead, please. Should I?
Hello.
Yes, anyone of either Dr. Ajay or Dr. Farzana?
Okay. Methods used in this study. In the study, a predictive model was built for the total LOS of patients undergoing laparoscopic appendectomy, one of the most common emergency procedure. Demographic and clinical data of the 357 patients admitted at San Giovanni
You can leave that particular hospital.
that
That's
particular university hospital of Salerno had used as independent variable of the multiple linear regression model. Result: the obtained model had an R-square value of 0.570 and 0.570, and among the independent variables, the significant variable that most influenced the total LOS were age, preoperative LOS, presence of complications, and complicated diagnosis.
Thank you. So in this case, you can see like what was the dependent variable? Yes, all of you please type in the chat box. What is a dependent variable in this case? LOS. So they are predicting the length of hospital stay for patients who are undergoing the laparoscopic appendectomy. And what are the other predictor variable? Yes, please type all the predictor variable. Can I see the chat? Age, complications, yes. And preoperative length of stay and complicated diagnosis. Yes, true. So they have performed the linear regression. Now, if I go and see their result. So see, they have written this equation. Can you see the equation for, there is a beta 0. What is a beta 0 here? Yes, all of you please type in the chat box. What is a beta 0 here? Yes, it is an intercept. And what is a beta 1, beta 2, beta 3? What do we name this? Coefficient. Very right. And then there is an error or residual towards the end. Right. And these x1, what is x1, x2, x3? x4? Predictors. Agrees. In this case, probably x1 could be age, and then length. X2 could be preoperative length of stay. Yes, X3 would be presence of complications. X4 will be complicated diagnosis. So those are the variables. So this they have written it. Now, if I go down, so now they have written all these. So they have performed, like the basic aim of there was again to show how a multiple regression is written. So there you can see what they have written, like before creating a model, following 6 hypotheses must be verified. They have written hypothesis, but it's the assumptions basically. So there you can see what was a, yes, can someone read this?
The linear relationship between the independent and dependent variable can be checked through the scatter plot.
They have written scatter plot, but it can be checked with the residual. So, okay. Now in the second one, this I have not told you multicollinearity, because right now I am only telling you with a single variable. So multicollinearity happens when there are more than one independent variable. So leave it for now. Scatter, actually residual and scatter plot, generally they are not same, because in scatter plot you take the actual variable. Actual variable means, but you can have, in case of a residual, this thing, I'll tell you the difference between these two. Actually, scatter plot, kind of you can, no, they are not the same. Scatter plot and residual plot are not the same, but there are two ways to check for this, and I'll tell you both way. So if I go, this one, the independence of residual, Durbin-Watson statistics. This I have not told you. This I will tell you. Again, this you see the residuals have a constant variance. It is possible to verify it by building the graph, standardized residual against the standardized predicted value. This which we have seen in case of Jamovi, this graph. If you come and see the graph, and if I write residual plot, so the this residual plot is basically, so this is your residual and fitted. And this, yes, scatter plot and actually residual, Farzana, which you asked, like scatter plot and residual plot. Basically, a scatter plot is a diagram where in x-axis and y-axis you take. But by default, it gives you that plot. So yes, it is the scatter plot only. And then you can see here like residual and length of stay. So these assumptions he has written here. And then they perform the QQ plot also. So here you can see assumptions. The QQ plot is also there. So in assumption check, you have got Cook's distance. This we have seen. You have got like a collinearity. I'm not telling you. For autocorrelation, I'll tell you what is autocorrelation. Normality, for normality, we go for QQ plot and we go for the residual for the checking the linearity and the homoscedasticity. And then again, they have written like presence of outlier. So they have written like presence of outlier. The Cook's distance values always less than 1 guarantee the absence of outlier. Can you see this one? So they have checked for all these assumptions. And this has been published in the BMC, Medical Informatics and Decision Making. Okay. So I think it is a good journal also. So they have tested for all assumptions. I think they have for the linear regression. I'll tell you regarding the collinearity and Durbin-Watson statistics. So basically Durbin-Watson, if you see the autocorrelation, in the assumption section, I think I missed that. Just a sec. I was about to, but yes. When I was telling you the underlying assumption, so there should be independence of observation or Durbin-Watson statistics. So the value of Durbin-Watson statistics should be less than 2. But what is this Durbin-Watson statistics? Generally, this assumption is an assumption of autocorrelation. So what is autocorrelation? Basically what happens, like residual, if you, we call it as a independence of observation of residual. If you are measuring something, let's say if you are measuring the skin thickness with a caliper, initially what happens? Like we are not very much trained of measuring something. So the initial values will be very much correlated. Why? Because we are novice and we are very crude in measurement. But as we move ahead with the measurement, let's say we have measured 200 and 300 people, then our accuracy will be very much improved. So the residuals in the initial part will be correlated. because I am very crude in measurement, and residuals towards the later part will be again very much correlated. So this happens when you enter the data serially. If I'm entering the data serially, means the 1, 2, 3, 4 like that, then this problem might happen. And this problem might happen due to, like, if I'm not trained enough beforehand and I'm not certified enough beforehand to measure something. Similar thing happens with blood pressure. Like with automatic, it is okay. But if you are using anything where you have to measure something, with repeated doing, you improve your accuracy. So your residuals tend to be correlated. In the initial part, it will be correlated due to some error, and in the later part again, it will be related due to the highly accurate thing. So it should not be very much correlated, and that phenomena is known as the autocorrelation. But if your study design, if your study design does not have a dependent variable like this, then you need to test for this autocorrelation. Like length of hospital stay. Length of hospital stay is not something which is it is a very objective measurement. Means like it is measured in the hours. So there will not be the intra-observer variation. It is this autocorrelation is basically if your dependent variable which you are measuring, that will have an intra-observer variation. You know, there is an inter-observer variation and there is an intra-observer variation. Do you know these concepts? Yes, can I see the chat box? No. Okay, no is for 12:57. What is it now? Okay, Farzana, if you don't know, see, what is an intra-observer variation? Suppose you give me one task. Let's say, again, the same example. Any other measurement example I can quote? Like skin caliper, because I have done it.
Measurement of
Pardon?
fetal head, measurement of head circumference of fetus in ultrasound.
Okay, so maybe I do not know that, but again, do you think that it improves with accuracy, like when you do it repeatedly?
It can while doing a scan for a fetus, it can vary when the same person does it. Also, it can vary,
Okay.
and it can vary with the different operators also if not performed appropriately. So we give a margin for intra-observer variability and inter-observer variability.
Okay, rightly said, Subhapriya. So good. But again, if the same person, even if the instruments are same, and if it needs like accuracy, means like you need to be very much precise. And this maybe you can see with the blood pressure. Blood pressure, when you do it with the mercury sphygmomanometer, then you need to hear that sound, two sounds, okay, appearance and disappearance of sound. So initially you are not very accurate, but the more you get yourself accustomed, your accuracy improves. So that we mean by the autocorrelation. Means something, your dependent variable is something where there are, like, initially, because of the my crude way of doing it, I was doing all wrong. All wrong means it was not very accurate, but they were all correlated. Why correlated? The variations were less, they were all correlated. But during the later part, those again they were correlated, because now I am very experienced in doing it. So the later part of my like measurement, it was again correlated. So this happens when it is a study design issue. So my dependent variable here in this case, although they have done it, the Durbin-Watson statistics, but if my outcome variable is the length of hospital stay, then there are no chance that it will be correlated. Why? Because it is not related to the measurement accuracy or something like that. Length of hospital stay is something when the patient has come and when the patient has gone out. So probably Durbin-Watson statistics is not always checked. It is only checked when whenever you are your dependent variable, when you are measuring it, and there is a chances that the like serial number like 1 to 10 or 1 to 20, all the measurements will be highly correlated. The errors, it is not related to the measurement. All these we are performing on residuals. So the residuals will be highly correlated. And that should not be there. So that we check by the independence of observation. And this is the independence of observations of residual. Means the one residual will not give you value of any other residual. And that we mean by the independence of residual, which we check using Durbin-Watson statistics. And the value of this Durbin-Watson statistic should be less than 2. Okay, that is the concept of autocorrelation. So this, I think I could not tell you at that time. So this is the data. Now let me see the question. So first I have to, so this we have shared with you people. So again, the background is like laparoscopic. This is, we have taken the base of this article only. So laparoscopic appendicectomy, it is a common surgical procedure, and same introduction I think we have written. So problem statement is like, despite standardized care protocol, there are still some variations in hospital length of stay. An identified predictor for a longer length of stay can help clinician to optimize care, anticipate resource needs, and improve outcome. So what is the research question? What clinical and demographic factors are associated with the length of stay, hospital stay in patients undergoing laparoscopic appendicectomy? And these are the variables. So the length of stay is a continuous variable, age is a continuous variable, gender is a categorical variable, and we have given the code also. So 0 is for female and 1 is for male. Pre-op length of stay is an integer. It is the number of days stayed before surgery. Complications are all categorical. 1 for complications occurred and 0 for no complications. And complicated diagnosis, again, categorical. This is while at the time of performing the surgery. So this categorical is like 0 and 1 is for there. So complicated appendicitis diagnosis is 1 and 0 is uncomplicated. And all the comorbidities, like 0 is for absent, and they have given 0 as none. And even if one of the comorbidity is there, they have given a code of 1. And the other individual comorbidities were heart disease, diabetes, hypertension, obesity, peritonitis, and cancer. So again, you can see the descriptive statistics of the variables. And then again, you can see the age distribution and all. So I'll go to the data set now. So this is the data set. I'll remove all this analysis, all remove. So this is the data set. First, I'll go with the exploration, means I have to check for the descriptive. So I'll go with this descriptive. I'll just see, because in here also, if you see the table, you have to give the descriptive statistics. You can see the frequency of comorbidity. They have given like heart disease, diabetes, hypertension. What is the frequency of comorbidity? Again, if you come here, all that frequency, what is the data, the overall 357 data set, they have given the complications, not or yes. And then the preoperative LOS, they have given the mean. And LOS again as a mean. So these are all descriptive. So in linear regression also, you need to give a table of descriptive statistics. So I'll go to this. So I first, you may go with this categorical variable. Age category we have created. We have shared the same data set. This data set we have created for this workshop. And you can click on this frequency table. So you uncheck all this, otherwise it will give you this table. So this male and female, there are 200 male and 155 female. If you see the age, 238 people are less than 40, 64 are like between 41 to 60, and above 60, 55 people are there. If you see the percentage, these are the percentage like 67%, 18 and 15%. If you see the complications, like 90% were having no complications and 10% having complications. If you see the complicated diagnosis means complicated appendicitis. Then 61% were having no complications, complicated appendicitis, and 39% were complicated. If you come down, these are the other comorbidities. So just the descriptive statistics. And for continuous variable, how do you do that? So all these variable. Okay, so I'll just copy this analysis, duplicate this analysis. So if you duplicate it, it will remain. Otherwise, if you move these variable back, all this will be gone. So I have moved all these variables here. Now continuous variable I'll take here. Age, pre-op, and I need to click this. You can see mean, median, maximum standard deviation. You can see the range. And other you can also take like percentile and all, but if I only take, so here you can see like this is age, mean age was 38.37, median this standard deviation range and all. So these are the two continuous. So they have given like the mean of these variable, like length of stay and the length of stay, the mean length of stay and the preoperative length of stay, these two. So in the single table, they have given in the two tables, they have given the descriptive and the of mean and categorical variable. And I think they have performed the analysis in IBM's 27. They have used the SPSS, but the same thing you can do in the R also. Not R means Jamovi. I think so. That will be heavy for them. So should we break for lunch? Then I'll